talk on combining structured and unstructured knowledge from Toshiba University. Several authors are here, and Svetlana will be giving the presentation.
Good morning. I will be presenting our work on using different types of knowledge in dialogue systems, and this is work done with my collaborators at Toshiba Europe, Suraj Kamdi, Simon Kaiser, Norbert Brunschweiler, and Raman. In this work, we are applying our methods to interactive search tasks. So interactive search task involves finding information, finding entities in either structured or unstructured data sources. So it could be searching for restaurants or hotels, or in a different domain like manufacturing. It could be finding tools and so on. And this task can be approached from different perspectives. So in dialogue community, we usually build natural language interfaces that interface for curated structured resources such as databases. On the other hand, we may approach it as information extraction, which allows you to search using natural language from unstructured resources. And in this dialogue community, we create schema-driven dialogue systems that provides natural language interface to this database information. While in the information extraction community, this interactive search involves adding interactivity to natural language search interfaces. So the goal here is to combine the two approaches, and so in the schema-driven dialogue systems that we work on in dialogue community, the system first detects intent of the user or actions in the user's utterance. And for example, in our work, we use restaurant search as the domain. So the system allows the user to specify properties of the restaurant, such as food type and area and price range. So user might say, find an Italian restaurant in the center. And next, a domain act detection or dialogue state tracker would detect slots in the user's utterance. And if the user's utterance intends to search for an entity, is providing an informed slot like Italian restaurant in the center, this would trigger a database lookup, resulting in matching items. And dialogue policy would then decide whether to present information to the user or ask a clarification question based on the confidence of previous components. And the advantages of this approach are that it allows us to bootstrap the dialogue manager from database structure. We can create natural language understanding components by creating utterances for slots, for specific slots that we expect in the user to provide information for. And we can create that natural language generation using templates. And for the policy, we can either create a rule-based policy or train a dialogue policy with a simulated user. However, the limitations of this approach are that it only handles in-schema requests. So if a user says something that is outside of the database schema, and the user who may not know what is the underlying database schema is, may search for something more flexible. Like, I would like a great place to watch a sports game on TV. Anything that serves fresh burgers and good beer. So this type of utterance would not be handled by a schema-driven dialogue system. And user in these systems are limited to providing fixed criteria. So when they provide food type, then they can find information, but not when they provide flexible information in their utterance. And in our previous work, when we were giving users flexibility to specify their search queries without limiting them to specific goals, we found that in majority of cases, the users would specify something that is outside of the structure in this particular domain, restaurant search. So the proposal here is to extend the schema-driven system with handling out-of-schema search queries. So on the left-hand side, we have the legacy component, or the component that processes utterances that contain structured information, contain food type and area, or price range, and perform database lookup and extract matching items. And the new component that we introduced is component that processes out of schema utterances, such as find the romantic place that serves great wine. And in our work, we utilize external unstructured resource, and we use reviews that were written for the restaurants by people. So we use relevance ranker to we apply semantic similarity in order to rank the restaurants according to the user's query, and the ranked items are then intersected with the matching items in the database lookup, providing the resulting set of items. So we collect more up-to-date database set of restaurants, which is 422 restaurants in Cambridge. So in the ideal scenario, this would be the data set that's constantly updated and pulled on regular basis to be up to date. But for research purposes, we extracted a fixed set of restaurants. It has the similar structures, previous versions of the systems in DSTC competitions. So they have name, cuisine, price range, area, phone number, and address. In addition to that, the each restaurant has snippets associated with them. And the snippets include information such as meals, whether it has breakfast, lunch, or dinner, special diets, such as vegan-friendly, gluten-free, and most of the snippets are reviews. So reviews, there are 147 on average per restaurant, but it really ranges. So some restaurants have almost no reviews, and some have a large number of reviews. So that's why we decided to keep meals and special diets in the list of snippets, although you could argue that you could make them part of the database structure. And these are examples of snippets I was it was such a happy surprise that they allowed dogs inside their premises. So we assume that this would be useful for a query if a user wants to find a restaurant that allows dogs, which some pubs do in England. So in the new component that we introduced, we have intent classifier, which classifies user utterance into 3 categories. It's either a search query, an information request, or something else. So if it's a search query, we would apply the relevance ranker, generating a list of ranked items. So, and for an utterance, find the Italian place that serves great wine, the domain specific component would extract all the Italian restaurants, and the ranking component would rank them according to presence of reviews that have great wine mentioned. And so info requests are utterances that request information about the restaurant, and at this moment we would normally handle them with question answering component, but at the time of evaluation we did not have that yet in the system. So the 3-way intent classifier distinguishes between a search query, such as find a place that serves great wine, versus information requests, do they serve wine, versus something else that the user can say, such as sounds great or not my taste. And while we don't have a way to handle these utterances because they don't trigger access to the database nor response with any kind of information, we still need to recognize when the user says something outside of the search query or information request in order to have a coherent conversation. So we do this at the moment with a template. We detect sentiment, positive or negative, and generate template-based utterance and response. So we build 3-way classification using BERT model, and initial data set that we use is constructed from previously published data. So we use SGD, schema-guided dialogue, for utterances that represent search query class and other class, for which we use affirm, select, and negate. We use DSTC9 for information request utterances. And once we build that system, we collect data, a small amount of data internally. And but when we trained it on, when we annotated the data, we saw that the classification was 71% of the on the intent detection. So we combined the collected data, which we annotated, and the data from SGD and DSTC9, and that gave us good performance of when we evaluated on a 10-fold cross-validation. And here you can see the distributions among the intents. So in the final data set, we have a bit above 30% of search queries and quite a few info requests, and all of them have about 12% of other utterances. So relevance ranker first scores semantic similarity between the user's query and each snippet. So we encode query and snippet with sentence BERT, and we measure cosine similarity between them. So then we compute the score for each restaurant, which is a mean score of the top M snippets for this restaurant. And then we rank the restaurants according to the score, returning top N restaurants. The system then presents the first restaurant, and also in order for the user to see whether the information this restaurant is relevant, we append the snippet to the utterance. We perform human evaluation using 3 conditions. So our baseline condition is a basic schema-driven system, which does not have intent classifier for out-of-schema utterances, does not have a semantic ranker, and it does not include snippet in the offer when the system presents information. We collect data using mechanical Turk, and we use unscripted goals. So typically in this kind of evaluations, the users are given specific goals, such as you want an Italian restaurant in the center. So in this work, we're actually interested in users specifying a range of different queries. So we ask them to find restaurants of their choice without telling them what to look for. And we collect 81 dialogues per condition. And our hypothesis is that semantic ranker would outperform both schema-driven and random ranker condition. So random ranker condition is a control condition which we introduce in order to determine whether users would prefer semantic ranker because of the presence of intent classifier or because of presence of semantic ranker. So the random ranker differs from experimental condition is only by not having semantic ranker component. So we just use random ranking for this condition. We ask the users subjective questions to judge. We asked them 5 subjective questions, whether they were able to find a satisfactory restaurant, whether the description matched their preferences, whether the system understood them, conversation felt natural, or and if they would recommend the system to friends. So we observe that on all of these statements, the semantic rank system is rated the highest. And we also can see that random rank is rated only slightly higher than schema-driven system. So we also look at objective metrics. So as objective metrics, we look at dialogue length, average dialogue length, success criteria. So at the end of the questionnaire, we ask the users to enter which restaurants they chose or write none if they didn't find any restaurants. And we measure proportion of users that actually selected a restaurant. And we look at start over rate. So start over rate, users were allowed to say start over if they were stuck. So we want to minimize the number of start overs. We expect that would lead to a better system. So we here again observe that semantic ranker achieves the highest success rate and the lowest dialogue length. And interestingly, presence of dialogue act detection, which is present in random ranker, also reduces the dialogue length, start over rate, and increases the success rate. So it's interesting, but we did not see this in the subjective questionnaire. In subjective questionnaire, the semantic ranker outperformed the random ranker. So we think that this is because of the dialogue act detection, even though the system doesn't present the user with correct matching restaurant, it still benefits from being able to detect the dialogue act of utterances that don't contain structured information. So to summarize, we proposed a hybrid design for information search dialogue system that supports utterances like find a romantic place that serves great wine. We performed mTurk user evaluation with unscripted goals and showed improvement in both subjective and objective metrics. And in our future work, we plan to extend the system with question answering functionality and explore the use of different data sources, in particular, looking at different levels of structure, such as exploring discussion forums and social media posts. Thank you.
We have time for some questions. Mike, you want to start us?
Hi, is it on? Is it on now? Okay. Hi, Mike White from Ohio State University. This is really nice work. It's super interesting, but one question I have is whether you've thought about, how best to present the information from the reviews, because the database is presumably curated objective knowledge, whereas the reviews is opinions, right? So you might have one user that says this is great, even better than Tesco's Finest, the wine, but you might have lots of other users saying, oh, I was really disappointed in the wine. And if you pick just the one review that, if you, without even saying, one person found, right? So there's a question of accuracy there. So presumably you didn't actually ask your Turkers to go to the restaurant and report whether they liked it or not.
Right, yeah, that would be the ultimate test, but we could not do it, unfortunately.
Have you thought about ways of presenting that to
Yes, that's
reflect
a
the
great
fact that their
question.
opinions?
So that I think that's almost like a different, another research area, how to pre-process data and how to organize the data. Right now, we just took the reviews and we treated them as a knowledge base without any pre-processing, except that we only pick high ratings, only reviews that were ranked 4 and 5. And the reason for that was because we assumed that the user would look for something positive in restaurants. So we were focusing on positive reviews, but that's definitely an avenue for future work if you want to create a realistic system that provides value to the user and gives analysis of actual properties of these restaurants. I think there's definitely work to be done in that area.
Great, thanks.
Just follow up on that on the using positive reviews only. Even though you want to make recommendations, it seems like negative reviews would still provide a lot of valuable information for pruning. Like if it says it has great wine, but it has a terrible atmosphere, it's a dive bar, it seems like it might be a pretty good match, but it's really not given all the criteria or pruning things out.
Yeah, that's true. I think if you want to do it properly, you need to really process all reviews and like maybe generate kind of a summary of so it would not be unstructured data anymore, but more structured data automatically generated. So I think for realistic applications that may be the way forward.
Hey, Svetlana, Matthew Marge, Army Research Lab. I really liked the talk. I was wondering if you did any error analysis. Really, I wanted to see if you thought the errors in the semantic approach were any different from the schema approach, and maybe there's some obvious choices of what you might see there.
Yeah, so we have not yet analyzed the errors on this data set, but in our previous work, we looked at the analysis of relevance ranking, and this approach achieved quite low scores. It was about 66% accuracy in comparison to supervised approach. So we also had a supervised model which performed, I don't remember now, but in somewhere in the 80s. But that wouldn't be feasible for in real-time system. So definitely improvement on the ranking of relevance is another avenue of research. Yeah.
I think we're out of time, and we're a little behind schedule, so I have to pick it up. Actually, our next two talks have questions.